afternoon, everyone. Welcome to the seminar for 15 RDE 001 certification and in-use testing for heavy-duty diesel engines to understand high in-use NOx emissions. Before we get started, I want to let everyone know if there is a fire alarm, everyone has to exit through these exit doors, and the evacuation point is the Cesar Chavez Park, which is just across the street. This we have this contract with UC Riverside, CSUT. It started in 2015, and we just finished this project. And in this, here is a brief introduction about the project background. NOx is a major pollutant emitted by diesel engines. The figure on the left side is a very simplified sketch of a diesel engine. NOx is formed from the high temperature combustion in the cylinder. Advanced engine designs can manipulate the in-cylinder combustion dynamics to reduce the engine out NOx. For example, electronic control of fuel injection timing could change the engine out NOx. Advanced fuel injection timing or early fuel injection that can increase the combustion pressure and temperatures. And this can improve the fuel efficiency, reduce PM formation, but it can also increase the NOx emissions. Retarded fuel injection or late fuel injection has the opposite effect. However, although there are many in-cylinder control technologies, these technologies are not enough to meet the 0.20 gram per brake horsepower hours NOx standard. So modern diesel engines typically use after-treatment systems, especially the selective catalytic reduction system, to meet the stringent standard. SCR system introduces aqueous ammonia to the catalyst, and that forms ammonia, and aqueous urea to the SCR catalyst, and which can decompose to form ammonia, and that can react with NOx over the catalyst, and ammonia will react with NOx to form nitrogen and water. The optimum catalyst temperature should be higher than 250 degrees C. On these conditions, copper zeolite catalyst can reduce more than 90% of the total NOx. Heavy-duty diesel vehicles certification is a very complicated process. The heavy-duty diesel engines are certified using an engine dynamometer. Engines are tested over the federal test procedure, which is called as FTP, and the supplemental emission test, which is called as SET. NOx emissions should be less than 0.2 grams per brake horsepower hour, or the applicable family emission limit, FEL. And engine dyno testing is using laboratory-grade instruments, so it has a very high accuracy and precision. For the vehicles, it has in-use compliance requirement. Engine-certified vehicles should meet the not to exceed NTE standard in real-world driving. Emissions are measured using portable emission measurement systems. These systems are less accurate compared to lab equipment. However, real-world observations show that in-use NOx emissions can be much higher than expected. On the right side is a paper just accepted from our group, which showed that in-use NOx emissions can be much higher compared to the 0.2 grams per brake horsepower hour in many real-world applications. And high in-use NOx emissions could be caused by many factors. For example, the difference between lab conditions and real-world driving conditions, and differences in load factors. All those could contribute to the difference, but we want to understand what's the exact cause of these differences in this project. As I mentioned earlier, heavy-duty vehicles have to meet the in-use compliance standard, the NTE standard. NTE requirements were developed back in early 2000, and it was designed to help ensure heavy-duty diesel engines in-use emissions are properly controlled. However, it's not a sufficient measure to control in-use emissions because it excluded a lot of operations. For example, low-load operations are excluded by NTE, and when the exhaust temperature is colder than 250 degrees C, those operations are also excluded. So the NTE requirements only controls a very limited area of the engine operation, and we want to evaluate if this through this project to see how effective is the current NTE standard, and we want to develop to figure out if there are other alternative metrics. So the objective of this project is to measure and understand the differences between NOx emissions on the certification and the in-use conditions for the same engine. We want to evaluate current and proposed in-use compliance procedures. In this study, CSERT tested 2 heavy-duty diesel engines from 2 different OEMs. Both engines were certified to the 0.2 grams per brake horsepower hour NOx standard. And they tested these engines on chassis dyno, engine dyno, and on-road. And they have some very interesting findings from this project. So Tom, I will give this, so now it's your turn, and you can talk about your findings.
All right, thank you, Yi, for the introduction and for the discussion. I do want to start out by just acknowledging that I had a number of collaborators on this study from UC Riverside, from graduate students to other research faculty as well that contributed to this work. So again, Yi gave a good background there. I want to give just a little bit of a different background. And, you know, starting out broadly, even a little bit more broadly, is that, you know, looking at health effects being very important and sort of driving what's going on here. And if you look at the national air quality standards, you can see that there's a lot of non-attainment areas, both for PM and for ozone. NOx in particular contributes a lot to ozone, as well as the contribution to secondary PM formation in urban areas. So if we look at California in particular and the LA basin, which really drives a lot of the some of the regulatory pressure in terms of reducing NOx emissions, you can see here that in 3 cases on the left-hand side, if you go from the base case to in 2012 to 2023 and 2031, you can see that there is significant progress being made over time in reducing emissions from different sources, and in particular from mobile sources. So mobile sources are sort of the sources that are blocked in that red box there, and you can see that there's a significant reduction there. But compared to the carrying capacity or the amount of NOx that can be emitted into the air in Los Angeles to still obtain the standard, you can see that you almost have to completely eliminate emissions from mobile sources to get there. So it's a very challenging problem that we're looking at, and also we can obviously see that the heavy-duty vehicles and trucks and also the non-road, which represent the top part of those bars, are a key part of making those reductions. So another important thing is that, you know, relative to the certification standard that the engines are certified to, generally it's been found that the in-use NOx emissions tend to be higher than those for the certification testing. And if you look on the left-hand side of the sorry about that. If you look on the left-hand side of the slide here, you can see that these are some chassis dynamometer testing results, and this shows, the green bar shows where the actual emissions are, and the red sort of line indicates where they are if you were to expect them to basically meet the standards under all the different conditions. And you can see that as you go down there, you know, first of all, I don't think we want to overlook the fact that there is tremendous progress being made in reducing these emissions. But if you look at the difference between where the red, it's very sensitive, so let me see if I can. If you look at where that red line is relative to the green line, it does continue to have a bigger gap there as we go to lower and lower emission levels. On the right-hand side is simply looking into the future, and we look at the MFACT projections of what the gram per mile emission rates are in blue compared to the blue dashed line, or the red dashed line, which is where one might expect if all operation was at that 0.2 level. You can see that there's likely to continue to be a disparity between the end use and what one might hope for based on the certification. So this particular study, the idea here is that heavy-duty diesel engines are designed and certified to meet emission standards on an engine dynamometer test stand before the engine gets inserted into the vehicle. And so really we're trying to better understand that transition between the engine dynamometer testing and conditions to the in-use conditions on the same engine. So basically we took two heavy-duty vehicles and we looked at emissions under varying conditions, including in-use conditions, chassis dynamometer conditions, and engine dynamometer testing conditions. So the two vehicles were both 2013 to 14 vehicles that had engines certified to the 0.2 gram NOx standard. Okay, so the procedure for both vehicles was the same. We start off with the vehicle in the vehicle, or the engine in the vehicle and on the chassis dynamometer, and we run it over a series of cycles, and we look to see if the UDDS emissions are higher than 0.2 gram per brake horsepower hour. And once we've confirmed that, we do some additional on-road testing with our mobile trailer, and actually a lot of that testing was done simply with PEMS that were mounted inside of the trailer. Then the engine was pulled out and put on our engine dynamometer test stand and run through a series of tests. And then finally, the engine was put back into the vehicle to see that we were roughly able to recreate the same conditions that the vehicle was seeing once it came into the test facility. So this is a test matrix that breaks down the different types of testing that we did. So again, this runs somewhat chronological, at least in terms of the main methodologies here. So we basically did a chassis dynamometer test, and in doing that, we did tests that were representative of urban driving, including the UDDS test cycle, the CARB transient cycle, as well as freeway types of cycles that included cruise cycles at 55 and 65 miles per hour. So once that was completed, we took the vehicle on road, and here we had three on-road cycles that were predominantly highway cycles. I'll provide more information on that a little bit later in the presentation. And then we replicated the UDDS on road. And I'll be talking about that later as well. So for engine dynamometer testing, again, we did a series of tests. Some of them were FTP, UDDS type of tests that were more consistent with urban conditions. And then we did the ramp modal cycle and different cruise cycles that were basically adapted from chassis dynamometer data. And then finally, we returned the vehicle to the engine to the vehicle, and we run a follow-up chassis dynamometer testing. So just going over to the emissions measurements, we did try to look at the emissions with both our emissions trailer, which is 1065 compliant, as well as PEMS. So two different methods, except for the on-road, where we only use the PEMS, and the second chassis dynamometer, where we only use the emissions trailer. And then we also have different preconditioning. Most of these were run as hot running cycles, where we warmed up the vehicle immediately before doing the cycle, with the exception of the UDDS cycles and the FTP cycles. Those were all run as hot start cycles with 20-minute soak periods in between tests. Okay, so two manufacturers, we designate them simply as A and B. So this chart here shows the basically the whole gamut of cycles that we ran that we classify as urban cycles. And so these are the UDDS, the FTP, sort of the transient cycles, and cold start variations of those on the far left side. So we do most of the emissions we report from our emissions trailer, except for the on-road testing, where we basically only had the PEMS available at that point. So you can see here that, first of all, there is a wide range of emissions results as a function of the different cycles that we're looking at. Generally, the cold start emissions at the far left tended to be higher, not necessarily every cold start in all conditions, however. The other thing that I want to look at is first, if you look at kind of metrics for comparison, you know, obviously the certification standard at 0.2 might be one metric that you are looking to compare against. Again, we're not necessarily looking for this to be a certification substitute in any way, or, you know, it is a research program. And secondly, if you look at some of the in-use testing that is going on, or some of the in-use compliance testing that has been done by the manufacturers, you find that their average on-road emissions measurements have been somewhere around 0.37, in that 0.4 range. So in looking at those two metrics, you can see that our results do tend to be higher than the 0.2 standard, but they're not outrageously different from that 0.4 level when you look at the cycles as an entirety, and we'll be looking at a few more cycles in a few minutes. Then the green line across here is the SCR temperatures. So these are the average SCR temperatures, so different parts of the cycle will see different temperatures. On average, they tend to be above 200, in some cases also above 250, but in others between that 200 and 250 line. So the second manufacturer, again, we designate that as B throughout the whole presentation here. So here you're seeing generally a little bit lower emissions for these urban cycles. Generally, interestingly enough, a little bit lower SCR temperatures if you just do a direct comparison there. Again, you're seeing Now you're looking at the 0.2 level being that first line, and the 0.4 level being that second line. So we're not, we are still a bit above where one might hope to be based on the certification, but we're not, in many cases, outrageously outside of what one might expect. And I will note that the engines had, I think one engine had slightly over 100,000 miles on it. The second engine had about 220 or 30,000 miles on it. So they're not brand new vehicles or brand new engines here that we're looking at. Okay, so now let's move from the urban cycles to the cycles that are either freeway cruising cycles and or steady state, like the ramp modal cycle on the far right side here. So here, the red bars indicate 3 different routes that we ran on road. I'm going to go into more detail about that a little bit later. They were tended to be more hill climbing, and I'll get into that a little bit later. But in comparison with the urban cycles, you can certainly see that the emissions levels are lower, in many cases below the 0.2 certification level, and certainly below the 0.4 on an average for the freeway driving. Okay, so manufacturer B, again, some of the same trends that we're seeing with manufacturer A, generally lower emissions for the freeway type of driving. Here we are in the range of 0.2, maybe slightly higher or lower depending on the specific cycle, slightly higher for the on-road tests shown in red that we measured with the PEMS. And in general, if you look at those SCR temperatures designated by the green lines, they are by and away higher than what we found for the urban cycles. Okay, so now we're going to look at some of the different test sequences in a little bit more detail to try to understand what is going on in terms of this comparison between the engine and the chassis dynamometer and on-road testing. So we're going to start off just with the base FTP tests. So again here, the green line does show the certification. So at least for the engines we had in the laboratory, we were slightly above the certification standards for both engines. Again, that's not necessarily any indication of compliance. It's just kind of a baseline for where the engines were performing as they came out of the trucks at the mileages that we pulled them out. And there's some additional details related to manufacturer A and the engine testing that I'm going to get to in a few minutes as well. So secondly, we want to look at some of the comparisons between the UDDS cycle, and the interesting part there is that this particular cycle was done in all of the different phases. So we did a UDDS for the chassis dynamometer. We replicated that UDDS for the in-use testing, or on-road testing, and then also for the engine dynamometer testing. So I want to get into, sort of how that was done. Okay, so the starting point for all of the UDDS testing was the chassis dynamometer test. So we ran the chassis dynamometer test on our chassis dynamometer as the first test that we did. So to translate that into the engine dynamometer test, we basically took the RPM and the torque values and we just directly translated them so that when we ran the engine dynamometer test, we basically mimicked the torque and RPM that was seen when we were doing the chassis dynamometer test. So some of the other, just as a frame of reference, some of the other engine dynamometer cycles were not directly pulled from this particular engine. They were basically pulled from the ACES program, where there was a lot of studies done in terms of converting chassis dynamometer to engine dynamometer test parameters. And so for most of them, we pulled and utilized those cycles, but for the UDDS, we specifically looked at the engine that we were testing for this program to try to make it as close a comparison as we could. Okay, so for the on-road UDDS, we had to use a little bit different strategy. Again, you're looking for a place that you want to have a relatively flat road. You want to have a road where you can drive relatively decent speeds for periods of time that are several miles, and you want to not be in a condition where you've got a lot of traffic that's going to interfere with that driving. So, and you live in Southern California, so it limits your options somewhat in what you can do. I mean, you can't do a UDDS on the freeway. You can't do it in the middle of the urban environment because you're going to be right in the middle of traffic. So to do this, we basically went to the far eastern edge of the Palm Springs area to a place called Thermal, and it's just east and south of Indio, California, if you're familiar with that. And we basically looked at some of the agriculture roads that are out there. And so if you look at on the left-hand side of the screen, there's 3 different segments to the on-road testing here, denoted M1, M2, and M3. So what you can see here is that we did have to split the road up and run this as individual segments. There just simply wasn't a road long enough to do this in one single iteration, where you wouldn't run into traffic lights, you wouldn't run into any kind of traffic conditions. So for the first vehicle, we ran segment M2, and I think M2 was run second or first, and we ran that on the southernmost road here that we were working on, and then M1 and M2 were on the northern roads. And then for manufacturer B, we actually reversed that, and we found that M2 was easier to run on that top road, and we ran the others at the bottom road. So pretty subtle differences, but we'll see that that can make some differences when you look at very specific conditions. So in terms of the testing, I do need to point out that it's as you might expect, it's not a simple test to bring an in-use vehicle in, test it on a chassis dynamometer, pull the engine out, and put it back in, and it is an in-use vehicle. It is someone wants to use it, so you don't have all day or all year to work on this. So we worked with the manufacturers to the best we could. We did get, for manufacturer B, we were pretty much able to run the engine dynamometer testing without any fault codes. We weren't able to clear some dashboard or dash communication fault codes for manufacturer A during the engine dynamometer testing. So that certainly complicated things, and I'll be talking about that in just a little bit. And again, we had 2 different types of 1065 measurements that we were making. One was with our emissions trailer. The second was with the PEMS system. Okay, so now let's look at this UDDS test that was done basically, you know, in a similar manner between the different types of testing that we did. And so we're going to focus here on the comparison between the chassis dynamometer testing and the engine dynamometer testing. So, and here you can see that for both engines, we were a little bit lower on the engine dynamometer testing than we were on the chassis dynamometer testing. On road, it was a little bit different. You know, in some cases, the on-road was lower. In some cases, the on-road was higher than what we found on the engine dyno. So, okay, so let's look at manufacturer A. And again, we discussions, we did have the fault code related to the dash communication, and so we need to consider that in the results and understanding them. So here you can see that we did see higher emissions in the chassis dynamometer testing. This sort of points out where the higher emissions were seen. It's largely in that segment of time from 550 seconds and beyond in the UDDS. And you can also see, if you look at the red line, there's not a great deal of difference in the temperature profiles. So it didn't appear to be something that was really related to SCR temperature. Again, looking now at the engine out emissions, and this relates to some of the complications that we had with this dash communication. So we did find higher engine out emissions, or lower engine out emissions rather, on the engine dynamometer testing. Discussions with the manufacturer indicated that that was due to this dash communication, and you can see here how that affected the tailpipe emissions. And the issue with that dash communication turned out to be that it would basically retard the fuel timing. So you can see here that the chassis dynamometer fuel timing was different than the engine dynamometer fuel timing. So again, that was an issue that we had in making those comparisons. And you know, consistent with what you might expect if you're retarding the fuel timing, we did see that there was about a 7% difference in fuel use between the engine and chassis tests, with lower fuel use on the chassis dynamometer testing. Okay, so let's move on to manufacturer B and do the same comparison. So here we have, again, a lot of that difference in emissions is from a similar time period. SCR temperatures, again indicated by the red line, were slightly different, but not necessarily super substantially different. So we did see some differences in engine out emissions that also contributed there as well. We don't have as much data on the manufacturer B truck to indicate sort of timing and fuel consumption. You know, we did see lower CO2 on the chassis dynamometer testing, but we don't have all of the information that we can do some similar analyses for that one. So now let me turn on road. So here we're going to look at chassis dynamometer testing versus the on-road testing. And here we did see probably greater differences in that for manufacturer B, we actually saw lower on-road emissions than, or considerably the lowest emissions for the on-road testing. So here we're looking at manufacturer A, the UDDS, and here if you look at the cumulative NOx, the green represents the on-road and the red represents the the chassis dynamometer testing, and again, a lot of the difference is in that same sort of 550 and beyond test period. Here, there were some differences in the test temperatures as indicated by the purple and the blue lines. Not necessarily drastically different in terms of what you might expect there. And you do see that there's a little bit of a jump in the purple line, which is the on-road line. And that's primarily due to the fact that we had to sequence these things in a different order. So that does change things somewhat in terms of what we're looking at. So here we did see a little bit difference also in the engine out NOx as well, but the fuel injection timing was not an issue there. It just indicates that there's a lot going on with that and a lot of things controlling that. So, and you're looking at fairly sensitive levels as well. You're not looking at necessarily huge differences between the on-road testing if you just go back and compare the first and the second bars there. Okay, so for manufacturer B here, you can see that, again, I've tried to separate the three segments because we did the on-road testing in three different segments here. So you can see that it depended from test to test, but for this particular example, you look at the way the testing was done, and since the M1 was done after M2, it tended to start out at a slightly higher temperature. So interestingly enough, I mean, we've done this particular route for a number of years, and we've done a lot of comparisons over the years, or at least we've done some comparisons between chassis and engine, dyno, and found pretty good consistency. That comparison becomes a lot more complicated when you get down to these vehicles that are operating at very low NOx levels. So you can see here just these subtle differences with the lower starting out temperature, and then if you look at M3, you do start to see the temperature drop for the on-road more so than you do for the chassis dynamometer, just because of the sequence that you're doing. And we'll look at that and how that plays out in terms of NOx efficiencies in just a second. So here, no real differences in engine out NOx, so that's not contributing to it. But when you look at the SCR efficiencies, you can see just those subtle differences between running different segments. You know, significant NOx reduction there from the engine out levels in both cases. It's just slightly better NOx efficiency in the on-road case versus the chassis dynamometer case. And you can see that, you know, when you look at those small differences, they look bigger on a graph. Okay, so we did look at SCR temperature as a function, SCR efficiency, excuse me, as a function of temperature. So the left side of the graph shows the efficiencies of the SCR system. This is comparing the basically the engine out and tailpipe out NOx data, and NOx sensor data was used for this. So you can see here that in a lot of cases you're above the 80% efficiency level, but you can see that as you get to sort of these below 200-degree temperatures, you start to see that efficiency drop off. Nothing too surprising, and you can see that you know, we're certainly in the range of some of these theoretical curves here. So on-road testing, here we're now no longer talking about the UDDS, we're talking about the freeway driving portion of the on-road testing. And so what we're doing here is we're starting off at UC Riverside, and we're doing 3 different segments. One segment basically goes up the Cajon Pass to a city called Hesperia, and this is a pretty aggressive hill climb. Then you come down from the hill. There's a Hesperia to Indio drive, and here you're downhill coming down from Hesperia, but you do have some elevation change between sort of the bottom of the hill at Hesperia and Indio, and then there's the return route that we come back from Indio to our UC Riverside. So, this is part of what ARB runs in their in-use surveillance testing. They start over here in El Monte, and they do this route, and generally they look at doing this route in a single day. For us, we were stopping because we were doing a lot of different work down in Indio at the far left, far bottom of the screen. So these were segmented in different days depending on, you know, how we could do the testing conveniently and whatnot to get the on-road, get the UDDSs and everything done, given the constraints of the different test days. So it's not necessarily that we're taking this data and saying it's going to be consistent with or equivalent to the in-use compliance testing that was done, that is being done by ARB. And we're also taking the more aggressive part of the routes that are used by ARB in their in-use compliance testing as well. So you can see here that the bars in the box show the on-road testing over these 3 routes, and the comparison is with the other data points. Those are the chassis dynamometer cycles that we're running on our chassis dynamometer over freeway-like conditions, cruise type of conditions. And you can see on the chassis dynamometer, we're pretty much lower than what we're finding on road. But again, we're going up, we're looking at grades, grade change, a lot of different things when we go on road. And again, if you look at that 0.4 baseline here, or 0.37 baseline from in-use testing, we're not super far off that level, even when we go for the on-road, more aggressive cycles. So this figure here just shows different types of conditions that we observed during the on-road testing. The red bar on the left side shows basically the full trip emissions. Then the pink bar is the data that is generated in the NTE zone, and Yi showed that zone in some of the preliminary slides, but that doesn't necessarily indicate a passing NTE event because you have to stay in the zone for 30 seconds or longer. So the green indicates where the passing NTE events are, and then the blue indicates the range of where the failing, the emission levels for the failing NTE events. And in terms of the NTE criteria, it's kind of it's really based on having no more than 10% of the data on a time weight basis in this high region. So we're looking at, you know, less than 90% of that data, or greater than 90% of that data being in the lower region. So so we did look at this, and again, you know, we're not, it wasn't a compliance test. You know, we spread these out over multiple different days, but we did see for manufacturer A, for most of the routes, we did find passing values and sort of the pass ratio just based on the 90% of the duration being below the in-use threshold And then for manufacturer B, we did see a lower pass ratio, as you can see from the information here. Okay, so just in summary here, so looking at the different techniques, we did generally see the engine dyno results showed lower NOx than the chassis dyno. The engine out emissions played an important role for that. We did see some fuel injectant timing differences with manufacturer A that were related to this dash communication issue. And so we have to be very cautious, obviously, in interpreting and trying to understand that. So for the on-road data, we generally showed lower data on-road than for the UDDS than on the chassis. And both the engine out NOx and the SCR efficiency differences played into this. And so I think if you look at the totality of everything we looked at, you can say that there's a number of different factors that play an important role in understanding NOx differences under different types of operating conditions, ranging from engine out, emissions, SCR temperature differences, and efficiency differences, and also even how you are driving and transitioning between different types of driving. So with that, I'll conclude and open it up for questions then.
All right, any questions from the audience?
Thank you for the presentation. My name is Seungju from California Research Board with Research Division. So original objective of this study was to identify discrepancy, the emissions discrepancy between chassis, engine dyno, and real-world testing. So you found there are differences, and you kind of summarized it here. There are a lot of factors involved in those differences, but still, like I don't think it is a pinpointing why there are discrepancies. How are we going to resolve or narrow these discrepancies? Do you have any idea how these kind of findings can become a springboard for the next set of the investigation if needed? Or so how are we going to, how do you see the way we can reduce this emissions discrepancy between tests?
Yeah, so certainly, as my professor used to say, you always got to end with you need more research. And I think certainly this is a case where, there's a lot more to understand here. Clearly this was a starter study, a first step, I think, in doing this type of work and understanding those differences. There's a lot going on in on-road measurements now. I would say there's a decent amount of chassis dynamometer work. Probably that piece where you're adding in. I would say there's a decent amount of work going on in the chassis dyno and the on-road at this point, and understanding some of that. Making that connection with the engine dynamometer testing, I think, is something that still needs more work. Perhaps maybe a little bit more. Obviously, it has to be very controlled. You have to. You need to buy the vehicles probably where you can spend a good amount of time on the vehicle and really get into depth on the different things that are going on, and you know, be able to examine all the parameters that you're seeing, a subset of which we showed here, you know, engine operation parameters, SCR temperatures, all of these things are critical.
Thank you.
Any other questions? Seems like we don't have any questions from on the email yet. Okay. So if you have additional questions,
Let me ask you another question. This is Seungju again from the Air Resources Board. So, you know, at the end, what we really need is to reduce emissions at the tailpipe. I mean, the emissions from the other vehicles during the real-world operation, that is way more important for developing air quality strategies and strategies to reduce the emissions from the vehicles. Vehicles are going to be cleaner. 0.2 gram engines are currently the cleanest engine, and there are hybrid engines are coming out and lower emissions, and emissions will eventually go further down at the tailpipe. And do you see, and the emissions level will be lower than today, and do you see like there is a bigger discrepancy for those low emitting vehicles between real world emissions versus laboratory measurement? And if so, then what are your recommendations based on your first cut of the research?
So, you know, certainly the margin for these differences that we're seeing is becoming smaller and smaller. There's a lot of subtle things going on that can easily impact things in ways that are hard to predict, probably a priori, to really going out and you know, I don't think when the emissions levels were developed a number of years ago, you know, people would be thinking that we'd be spending millions of dollars going out and testing every condition that's out there. You know, so how do you look and try to bridge that gap? You know, I do think one of the things that I know ARB is looking at, as well as the engine manufacturers, is to try to take advantage of the sensor technology that's available now, and to basically utilize that greater potential set of information that's available from in-use vehicles, and, you know, somehow utilize that to identify conditions that might be issues, and you know, somehow be able to bridge the gap in that way, as well as to understand these emissions really on a much bigger scale than we're doing with what we're doing with the emissions measurements with the PEMS or the chassis or any devices. So I hope did I sort of answer your question?
Yes,
Okay.
but the other, I just kind of, you know, projecting our near and midterm future, then low NOx engine technology will be fully implemented to not only for the natural gas engines, for the diesel engines and low NOx engines will come out and running on the road.
Yeah.
And then are we going to see this the emissions discrepancy between the real world versus laboratory conditions?
Boy, I'm not sure. I'm going to stay away from that one and run to the bathroom, I think. That's a hot button question, I think. You know, I do think that, you know, looking at maybe a low NOx cycle, for example, let me not touch the low NOx engine, but let me talk about, say, a low NOx cycle. I do say as you start to look at controlling things up front with say, a low NOx cycle in addition to the FTP, that is going to lower the amount of variability that you're going to see versus these end-use conditions, and that you're covering sort of these low-level, low-load conditions and higher loads, and however they transition between each other, you know, hopefully that will bring things closer, at least in one sense, you know, irrespective of how low that NOx standard itself actually goes.
Hi, Tom. Enjoyed both of your talks, actually.
All right.
So, a real quick question. Could you, may have been out of the loop for a while, but the on-road and chassis, excuse me, on-road and chassis are probably based on per mile basis, and then the engine dyno is on a brake horsepower. How did you convert from one to another, or is there an automatic conversion?
So all of these, you know, the ECM, you can get all that information from the ECM. Yeah, so all of that information, and if you look at in-use testing with the NTE, it's all done on a gram per brake horsepower basis as well. So that information's provided, and you can use that. You know, you get it from the engine dyno, but you're also now getting it from the ECM at all points, so that you can. Right, all the parameters that you need to calculate brake horsepower hour are available through the ECM at this point in time. Yeah, and you need that to do your NTE testing. Yeah.
A question from Tom Montes. On slides 37 and 38, can you explain why the correlation is much stronger for OEM A versus OEM B?
Okay, so these are the two slides that I put at the end here. Just for information's sake, I did not cover them. This is basically looking at what we saw with our PEMS measurements versus what we saw with the NOx sensor that was measuring the SCR out NOx emissions. So you can see that there's a fairly good correlation for manufacturer A, you know, with a R squared of almost 0.9 and a slope of about 1.6 or 1.06. So here you do see the R squared is not quite as good for the manufacturer B sensor. I don't remember which of these was the 2013 versus the 2014. I do think that this sensor technology is continuing to advance fairly rapidly in terms of the accuracy of these sensors. And, you know, I mean, I think the data I'm hearing right now is typically most of these are within 15% or better in terms of the sensors. So, you know, I think as you know, there are some specific differences here, but I think, again, as time goes on, I see those differences shrinking and, you know, being inside of, say, that 10% window.
All right, another question is, what's the time while the NOx sensors offline removed from the data set before you plotting the comparison data?
I believe so, yeah. Yeah, no, this is...
And the question, oh, this is a very long email. from someone anonymous. Were engine A and engine B placed in the same chassis for on-road testing?
No. Each one was its own individual truck. Yeah.
All right, so the second question is really related to that because the slides indicate chassis 1 and chassis 2. Assuming chassis 1 and chassis 2 were unique to each engine, then was the real gear ratio the same? What about the transmission, the tiles, and the driver? Are they
So
the same?
the driver certainly was the same for all of the driving testing. In terms of the transmission ratios and stuff like that, I don't know off the top of my head. We have that data somewhere, but it's not something that I think we looked at in great detail.
I will read this. Dr. Durbin acknowledged that driving style makes a difference. The GHG regulations confirm that tile types makes a difference. Obviously, gear ratios and transmission ratios put the engine at a different load, and the aerodynamics of the tractor cab makes a difference in frontal area, which adds or subtracts from the load on the engine, especially in the pump springs, which is home to wind farms. It isn't clear how this comparison was useful without exact parity in the chassis. Have any?
Okay, so, well, I mean, to a certain extent, we tried to, the comparison here was not necessarily to look at manufacturer A versus manufacturer B. So if certainly there were some differences there, but that's not to indicate any broader conclusions between those two manufacturers or any manufacturers. Really what we wanted to do from a research perspective was just try to understand what was going on between on-road or in-use conditions, be it with a chassis or an on-road test versus what was going on in the engine dynamometer. And so obviously for the on-road testing, the same truck was used for each engine had its own truck, but that truck was used throughout the testing. So the gear ratios, transmission ratios and everything within a given manufacturer should be the same, And I will note that these engines were in about the 11, 12 liter category in terms of size. So just to give people ideas there. Broadly, we certainly aren't making any kind of definitive decision about one manufacturer versus another. That certainly wasn't what we wanted to focus on in this. It's just we did see some differences over the routes, and we just pointed those out. So
there is a comment, not a question, from Mike Baker. He said he wants to mention that while there are not many people in the room, there could be many watching online, and he wants to thank you for both presentations today.
Okay, thank you.
All right,
take that one.
Yeah. Okay, I think that's what we have for today. Do you have any last-minute questions or comment? All right, I think that's it. Thank you all for coming to this seminar, and also thank you for those watching online. Have a good afternoon.